In all of the series we have dealt with so far, we have looked at series that have all of the same sign on all of the terms, specifically all positive terms. Because anything we can say about a series that has all positive terms can easily be extended for a series that has all negative terms. Certainly, a series that has positive terms that converges to a value. If the same series where all the terms are negative exists, then that would converge as well to the same value but negative. In this video, we're going to talk about alternating series. Alternating series specifically alternate between positive and negative from one term to the next. Now, there are series that do not alternate, but do include a mix of positive and negative terms. We will not be discussing those in this lesson. We will be considering only series specifically that alternate. Alternating series, that alternating sign is typically created by one of the following mechanics. -1 to a power, and that power may start as an even or odd power. So again, with all series assumed to be starting at I equals 1. -1 to the I would be -1 to the first, and therefore the first term would be negative. Whereas, if it was -1 to the I plus 1, that would be -1 to the 1 plus 1, or -1 squared, which would give us +1. In this case, the first term would be positive. After that, each increase of 1 in the value of I, as the iterative variable does in a series, will cause the power on the -1 to flip-flop back and forth between even and odd, and thus create the alternating sign. More rarely, but occasionally, you may also see cosine of I times pi. Remember that cosine at integer values of pi, integer multiples of pi, will always have the value of +1 or -1. So in this way, when I is 1, we have cosine of pi is -1. When I is 2, we have cosine of 2 pi, which is +1, and so forth. It can be done with sine, although that becomes a little bit trickier to do because in order to have sine be +1 and -1, it needs to happen at odd multiples of pi over 2, which you can see is going to become a little bit more difficult because having to do specifically odd multiples of the fraction of pi, as opposed to cosine, which is just integer multiples of just pi, it is possible to create the alternating sign in these ways. That being said, the vast majority of the time, we will see our alternating series formed by the -1 to a power. Now, the alternating series is going to work a little bit differently than the other series that we've dealt with. So let's look at some of the mechanics of it. First of all, is going to be the idea that we can separate the idea of the alternating sign from the actual value of the term itself. So an alternating series will typically be in the form of the sum from 1 to infinity of negative 1 to the I times a sub I. In this way, we let the negative 1 to the I handle the alternating sign, and the a to the I simply provides the value. Of course, this can also be from 1 to infinity of negative 1 to the I plus 1 times a sub I. The only difference between these is whether the series starts with a positive term or starts with a negative term, after which, though, it will simply alternate signs. For example, the series that I gave above is the series with I starting at 0 of negative 1/2 to the I. When I is 0, we have negative 1/2 to the 0 power, where any non-zero number to the 0 power is 1. And then we have negative 1/2 to the first, and then negative 1/2 squared is 1/4, because negative times itself is positive. And then negative 1/2 cubed will give us negative 1/8, and so forth. This can also be written, if we choose, and often we will, this can also be written as negative 1 to the I times 1/2 to the I. And in that way, the alternating sign mechanic, the negative 1 to the power, is separated from the component that provides the value of the term. There is then a special test for alternating series. It is appropriately called the alternating series test. We're going to suppose that the base value of every term is positive. In that case, the alternating series, whether it starts positive or starts negative, whether it starts positive or starts negative, these will converge if the following conditions are met. First, like any series, we need the terms themselves to be decreasing in magnitude. And more specifically, they need to be approaching 0. So what we need is first, the limit as I approaches infinity of the magnitude of the term. Again, not concerning ourselves with the sign here. We need the terms to be approaching 0 the further out in the series we go. This is the divergence test. Or the equivalent of the divergence test for an alternating series. So like any series, we need to pass the divergence test. We need to show that there is a chance at convergence based on the idea that the terms are getting smaller and smaller as we go and approaching 0. The second condition, then, is simply that each new term must be smaller in magnitude than each previous term, or at least no larger than it, for all I. For the beginning of the series onward, each successive term has to be smaller than or equal to the term before it. These are the requirements for the alternating series test. We'll do a proof, which is relatively brief here. We're going to prove it for the series that starts with the positive term. It is incredibly easily adapted for a series that starts with a negative term. What we're going to do is, as with the basic form of most series, is we're going to look at the sequence of partial sums. Most specifically, because of the way we need to prove this, we're going to look at not S sub n, we're going to look at S sub 2n. So in that way, we guarantee that there is an even number of terms. This is going to give us a sub 1, or again, by the very nature of negative 1 to the I plus 1, when I is 1, we have negative 1 squared gives us a positive first term. And then we're going to have minus a sub 2 plus a sub 3 minus a sub 4 plus a sub 5 minus a sub 6. And this is going to continue until the last pair of terms. The very last term is going to be a sub 2n. And because of the fact that we have an even number of terms as guaranteed by 2 times whatever n is, that last term will be negative, which means the one preceding it, a sub 2n minus 1, will be positive. What we can do then is, by the associative property of addition, is we can group these terms together in pairs. I can take a sub 1 minus a sub 2 and pair them together. And then I can take a sub 3 and negative a sub 4 and pair those together. And I can do this all the way down the line. Right up to the very last pair, a sub 2n minus 1 minus a sub 2n. Now, under the assumption that the second condition here, that both conditions are met, that the terms are approaching 0 and that each new term is smaller than or equal to the one before it, that means that if a sub I plus 1 is less than or equal to a sub I for all I, then that means that by subtracting a sub I plus 1 from both sides, we know that a sub I plus 1 minus, or I'm sorry, a sub I minus a sub I plus 1 is got to be positive. So what we have here is a series of positive terms. Now, the best we can say is non-decreasing. It is possible that there are successive terms that are equal to each other. That's why a sub I plus 1 is less than or equal to a sub I. So it's possible that one of these pairs in parentheses is actually equal to 0. In that case, we can't say that the partial sum is strictly increasing, but we can say that the sequence of partial sums is non-decreasing. Now, with this in mind, we can do another thing here. We can also take s sub 2n and rewrite it in another way. In this case, what I'm going to do is I'm going to group the terms again in pairs, but this time I'm going to do it by leaving a sub 1 out by itself. Now, with each pair set up like this, I can then factor a negative 1 out of each pair, and rewrite this in a creative way. S sub 2n is equal to a sub 1 minus positive a sub 2 minus a sub 3 minus positive a sub 4 minus a sub 5, etc. The idea here is that, as before, if a sub I plus 1 is less than or equal to a sub I, then the difference between subsequent terms, successive terms, is positive. That means what we have here is a positive value, a sub 1, and then from it, we are going to subtract another positive value, and then another positive value, and so on. This means that the sequence s sub 2n will always be smaller than or equal to a sub 1. Actually, that should not be the sequence. We should say that s sub 2n is less than or equal to a sub 1 for all n. No matter how far out we go in the series, we will only be subtracting things from a sub 1. What we have then is that the sequence of partial sums is bounded above. If we have a sequence that is monotonic and bounded appropriately, in this case, non-decreasing, meaning it gets bigger or stays the same, but it never gets smaller. If it continues to get bigger and has is bounded above, that means there's a point at which it can no longer get bigger. So it is sandwiched between its previous term, it has to get bigger than its previous term, but it is sandwiched between that and the upper bound. So in this way, we have that the sequence of partial sums is convergent. Now, again, as with most series, we're not particularly concerned with what it converges to, just that it does converge. Now, it is trivial to adjust this for a series that starts with negative term, and that literally becomes just every single sign in this changes. So, for example, in the case of a series that starts with a negative term, we would have negative a sub 1, and then positive a sub 2, and then minus a sub 3, plus a sub 4, and so on. All of these signs would simply change. In that case, we can easily deal with this by just factoring a negative 1 out from everything, and the whole thing works exactly the same, except because of the negative, it would change the sequence of partial sums to be non-increasing and bounded below. So if it's non-increasing and bounded below, then it also converges. So the adjustment for a series that starts with a negative term is trivial here. So again, under the assumptions of the requirements of the alternating series test, that the terms approach 0 and that each new term is smaller than the previous term, or at least no bigger than it. Under those two assumptions, we have shown that the series of partial sums is monotonic and bounded appropriately. Thus, it must converge. Let's look at some examples where we can apply this. Let's consider the series negative 1 to the I plus 1 times 1 over I. Now, it is worth noting that without the alternating series component, without the mechanic that creates the alternating sign, this is the harmonic series, which as a p-series with p equals 1, we know to be divergent. But according to the alternating series test, we need to show first that the limit of the term without the alternating sign approaches 0, which certainly it does in this case. As I gets larger, the fraction gets smaller. We also need to then show that each subsequent term is smaller in magnitude than the one before it. Certainly, it is true that I plus 1 is larger than, strictly larger than, I. Therefore, the reciprocals have the opposite relationship. Again, one of the rules for reciprocals is the larger the value, the smaller its reciprocal is. So if I plus 1 is the larger value, then 1 over I plus 1 is the smaller of their reciprocals. These are the two conditions of the alternating series test. Thus, the alternating harmonic series, as it is known, does actually converge. Now that's an interesting point because the harmonic series itself diverges, and yet the alternating harmonic series converges. There are a couple of ways to go about looking at this. One of them is that the harmonic series is the exact threshold at which a series can converge or diverge. If the terms of the series are even just a little bit smaller, even just a little bit larger than those of the harmonic series, it must diverge. The direct comparison test would show that. And yet, at least for P series, if the terms of the series are even just the tiniest bit smaller than those of the harmonic series, it's enough to allow the series to converge. So it is exactly on the threshold. What we should then realize is that the alternating harmonic series always is going to be smaller, or at least no bigger than, the original harmonic series. Consider this. Let's look at the first several partial sums. Let's look at just the harmonic series, which is going to be 1 plus 1/2 plus 1/3 plus 1/4, etc. S sub 1 here is, of course, just going to be 1. S sub 2 is going to be 1 plus 1/2, or 3/2. S sub 3 is going to be 1 plus 1/2 plus 1/3, which with a common denominator of 6 is going to be 11/6. S sub 4 is going to be the sum of the first three terms, 11/6, plus 1/4, which is going to be 25/12. Just a few of these to show what's going on here. Now let's consider the alternating harmonic series, which every other term will simply be negative. They're going to start with the same partial sum for S sub 1 because they both start with the same term of 1. But once we get up to the second term, we have to realize that now that in the harmonic series, we are always adding on. In this case, we're actually shrinking it a bit. So when we do 1 plus negative 1/2, we get 1/2. Our new sum is smaller than what we started with. We did show this as part of the proof of the alternating series test, that the sequence of partial sums will always be, of an even number of terms, will always be smaller than the original first term of the series. Now, we are then going to add on again. So when we are at an odd term, it's still positive. We're still adding on to what we had. But what we're adding on is smaller than anything we've dealt with so far. Therefore, what we're adding on is not even big enough to get us back to the original value of 1 that we started with. We're then going to remove again. This time we're going to remove 1/4, and that's going to give us 7/12. Now after that, we are going to add again. We're going to add 1/5. However, the 1/5 is smaller than anything we've done before, so we were at 5/6. If we prefer a decimal form of that, or we'll get an equivalent fraction for this, this would be 50/60, whereas 7/12 is 35/60. When we then add 1/5, that's going to add 12/60 back into it. That's going to give us 47/60. So while we did get bigger again, we didn't get as big as we had previously been. In fact, if we want to use a common denominator to more easily compare all of these, we went from 60/60 to 30/60, and then back up again, but not all the way up to 60. We went up to 50. We started with 60 in the numerator. We went down to 30. We did go back up, but not as high as the 60 we originally had. And then we went down, and then we went back up, but not as high as the 50 that we just had before it. So an alternating series is, by definition, always going to be smaller than a same sign, a single sign series. Or in the case of if we're dealing with a series that starts with a negative, it's always going to be larger than. But the point is that with easy adaptations for starting a series with a negative value, the premise here is that the alternating series will always be smaller. The partial sum of the alternating series will always be smaller than the partial sum of the same sign series, if you will. This is going to lead up to this concept of what we call absolute convergence and conditional convergence. We will get to that in a few moments after we look at a couple of other examples here. Let's look at another example of an alternating series. This time, this series is going to be, of course, starting at 1 as usual. And the series is going to be I over negative 2 to the I minus 1. Now, we don't have explicitly a negative 1 to a power, but we can easily get that through a little bit of algebra. The idea is, as long as the base of that exponential is negative, then what we can do is write it as a negative 1 times a 2 to the I minus 1, and therefore apply the exponent to each separate factor of the base. And in that way, we can draw the alternating component of it. Now, it is in the denominator, but ultimately all this negative 1 to the I minus 1 is doing is providing a positive or a negative sign, because the value of it will always be positive 1 or negative 1. It doesn't matter if it's in the numerator or denominator, because it's either going to be a multiplication or a division, and multiplying or dividing by positive 1 has the same effect. Multiplying or dividing by negative 1 has the same effect. So we can draw this out. And thus have our form of the alternating series where we can separate out the alternating sign mechanic from the magnitude of the term. Now, yes, we have an I minus 1, not an I or an I plus 1 in the power, but the fact of the matter is that as long as it is alternating, as long as it is progressing through integer values that alternate between positive or even and odd, it will produce alternating signs of negative 1 and positive 1. In this case, when I is 1, we have negative 1 to the 1 minus 1, or negative 1 to the 0, is equal to positive 1. So what this tells us is the first term is positive. And that's really all we need to know with regard to how the series is going to play out, is simply that the first term is positive. But even then, as far as the alternating series test goes, whether the series starts out positive or negative is not particularly relevant here. So let's look at the alternating series test. There are, of course, two things for it. One, the limit of the magnitude of the terms is supposed to approach 0. Now in this case, we end up with, in the top, I is approaching infinity, so the top approaches infinity. And in the bottom, we have 2 to a power that is approaching infinity. So we end up with an indeterminate form. But that being said, L'Hopital's rule will quickly show us that this does approach 0 because, as we've seen by now, the exponential function in the bottom is going to grow considerably faster than the linear function in the top. But a quick application of L'Hopital's rule will verify this. The derivative of I in the top is 1, whereas the derivative of 2 to the I minus 1 in the bottom is 2 to the I minus 1 times the natural log of 2. So as we can see, the bottom hasn't really changed, but the top has dropped to a 1, and that's enough to break the indeterminate form and give us a limit of 0. So we've passed the first condition of the alternating series test. We know that the terms get smaller as we go. The second part is perhaps a little bit trickier. Now, when I equals 1, we specifically have 1 over 2 to the 1 minus 1, or 1 over 2 to the 0. So when I equals 1, we have that the very first term is equal to 1. It's the magnitude of the first term. What we should note then is that for all subsequent values of I, we're going to reach a point where the numerator falls far behind what the denominator does. Because of this, and this is a weak form of proof known as induction, we can see that the denominator is simply going to outpace the numerator, and each new term will get smaller as we go, with the exception of the first two terms, which are both equal to 1. But it should be pretty easy to see here that the top and bottom are going to change at a rate that is clearly making these terms smaller as we go. Now, this is unfortunately a weak form of proof. We can see that this is the case here, and L'Hopital's rule does also help verify this. A more algebraic approach here would require a little bit more trickery. What we need to show is that I plus 1 over 2 to the I plus 1 minus 1 is less than or equal to I over 2 to the I minus 1. we would need to show that that is true. So let us assume that it is, and let us clean this up a little bit and make it I plus 1 over 2 to the I is less than or equal to I over 2 to the I minus 1. A little bit of trickery here. If we multiply both sides by 2 to the I minus 1, but if we also divide both sides by I plus 1, this will put the two exponentials on the same side, and it will put the two polynomial expressions on the same side. And we have here 2 to the I minus 1 over 2 to the I less than or equal to I over I plus 1. A bit of a simplification here on the left side. The denominator is always going to have exactly one more factor of 2 than the top does. So that simplifies to 1/2. Now, this actually does hold true for all values of I. When I is 1, the right side becomes 1 over 2. When I is 2, the right side is 2 over 3. When I is 3, the right side is 3 over 4. All of these things are actually bigger than 1/2 or equal to it. So from the very beginning, this is a true statement. And thus we have shown, whether it's through induction or through the more solid algebraic approach, we have shown that each subsequent term is smaller than or equal to the term before it. So between the two requirements, this passes the alternating series test, and this series converges. Now, we've seen two examples of alternating series that converge. Does that mean that all of them will? Not necessarily. There are, of course, alternating series that will not converge. One such example might be something such as 3 plus negative 3 plus 3 plus negative 3, etc. This can, of course, be written as the series negative 3 to the I plus 1. This will not converge because the magnitude of the terms does not approach 0. Oh, excuse me. This is a very bad series. I wrote that series entirely wrong. This would be the series -1 to the I plus 1 times 3. Clearly, the limit as I approaches infinity of 3 does not equal 0. In fact, the partial sums of this would be 3, and then 0, and then 3 again, and then 0 again. The sequence of partial sums is not going to approach a unique finite value. Thus, this is not going to converge. It is an alternating series, but it doesn't converge. And in this case, it doesn't converge because it violates the first condition. It actually does meet the second condition because the magnitude of the terms don't get any bigger as we go. But unfortunately, they also don't get any smaller. Another example of an alternating series that does not converge would be the series 2 over 1 minus 1 over 1 plus 2 over 2 minus 1 over 2 plus 2 over 3 minus 1 over 3 plus 2 over 4 minus 1 over 4, etc. In this case, this does pass the first condition because, as we can see, the values of the terms, if we ignore their positive and negative signs, the values of the terms are getting smaller as we go. That is to say, if we want to look at them in pairs, the numerators are alternating between 2 and 1, and the denominators in the first pair are both 1, and then in the second pair are both 2, and in the third pair are both 3, etc. That means that while the numerators are remaining a 2 and 1, the denominators are going to keep getting bigger. So eventually we will have 2 over 10 minus 1 over 10, and then 2 over 100 minus 1 over 100. These terms are approaching 0. However, this part is not true. Where we can see that is right here in going from 1/2 to 2/3. 2/3 is bigger in magnitude than 1/2. We see it again here, 1/3 going to 2/4. 2/4, or 1/2, is bigger than 1/3. We would see it again further and further out. We see it in this first case where these two are the same value, so that does maintain the idea that we are allowed to be, excuse me, that should be less than or equal to. We do maintain it here because it happens to be the same value, but in each subsequent thing, when we go from a numerator of 1 to a numerator of 2, we actually get bigger in a fraction. So we failed the second condition of the series here, the test. Now, it is possible that this series does converge. It is possible that it diverges. What we're showing here is that the alternating series test does not work. As it does turn out, both of these series, through other methods, can be shown to diverge.